All right, ladies and gentlemen, welcome back. This is the second part of Chapter 7, where we are talking about scatter plots and correlation. And in particular, this video is going to be all about correlation. The previous video, we talked about scatter plots. Now we need to talk about correlation. First, before we define what correlation is here, though, let's talk about really quickly about the roles that variables play. So it's really important that when you are working with a scatter plot or working with two quantitative variables, that you determine which variable goes on the x and which goes on the y axis. We make this determination based on the roles they play. For example, what you're generally looking for is which variable is kind of determining the other variable. For example, if you were talking about the scatter plot between like height and weight, does your height help determine your weight, or does your weight help to determine your height? So in general, we would say that height is an indicator of weight, and therefore we would call height the predictor variable, or sometimes the explanatory variable, and the weight would be the response variable, or sometimes called the variable of interest. Right? So height is the thing determining weight, and therefore weight would be what we call responding to height. Okay. The roles that we choose for variables are more about how we think about them than rather about the variables themselves. There are times when, or situations where time as a variable is explanatory. There are times when time is the response variable. So it's how it's being used, not necessarily the variable itself. Okay, putting it on a certain axis does not necessarily make it explanatory. It just means that you made a poor decision. Okay, so with that in mind, let's talk a little bit about this thing called correlation. So here we have a scatter plot of statistics students, height and weight. Okay, so height on the x-axis here being the explanatory variable, and weight on the y-axis being the response variable. And you can see with the scatter plot that we have a positive association. It is fairly straight, probably an outlier right here, right? We don't know for certain, but there's likely an outlier right there. But what can we say about the strength of this? How strong is it? And if we had to talk about strength, what kind of number would we put? Can we quantify how strong a association is between two variables with a number? And so if we look at these two things, we notice that height is in inches and weight is in pounds. If I were to rescale this graph, notice that the scales have gone different to centimeters and kilograms. Notice that it doesn't change the shape of the graph, right? That association remains the same. So strength is not determined by the units we use. In which case, we can get rid of the units. Right? If they don't matter, let's get rid of them. And remember, the way we got rid of units was to calculate z-scores for everything, right? So what you're looking at on the right here is the data that we just had, where we took all of the x values and we converted them to z-scores. And we took all of the y values and converted them to z-scores. And when you do that, notice that you still get a fairly similar looking graph, right? You can kind of see that shape in there. And as it turns out, the only reason why that shape is different is because the pattern looks steeper because we had to change the scale of the axes, because it was now 1, 2, 3 instead of the 85, 86, 87, etc. that we had out there. But the actual way that we made those z-scores, that scaling that we gave it, now gives it a neutral way of drawing the scatter plot. And it helps us give a fair impression of the strength of this association, right? So we can look at this, and it gives us a much clearer idea, maybe, of how strong it is. It also helps us quantify it with a number. We look at that now, and it's pretty scattered around. If you think about these as z-scores, right? We have a lot of z-scores within one standard deviation of the mean. We have less scattered around 2 standard deviations of the mean. And then this one up here is definitely clearly an outlier now because it's 5 standard deviations away from the mean. That's massive, right? So we can also look at these points now, and it kind of helps us determine what are these points doing, right? We have a positive association between them, and we can see like these green points, the ones in the bottom left and the top right, they are helping to bring this positive association. We have some red points here that are weakening that positive association, but notice that there's a lot less red points than there are green points. And then we've got blue ones that are on the axes that are just kind of zeroing it out, right? They're not really having an influence. So looking at those points, we have a formula that actually lets us calculate a number. Okay, so we're taking the sum of the product of all z-scores and dividing it by n-1. That gives us the R value here. Now, most times you will not actually have to do the product, the sum of the product here. You're going to use your calculator to find that correlation coefficient. Okay, but this number gives us a quantifiable strength of a linear relationship between these two variables when we actually go forward and calculate that. As it turns out, the heights and weights data has a correlation of 0.644. When you run it through that formula. So what does that mean? What does that tell us about the strength? Well, we need to talk a little bit more about correlation before we can really answer that question. So let's talk a bit more about correlation. First of all, there's some conditions that have to be met in order for us to use correlation. Correlation measures the strength of a linear association between 2 quantitative variables. If we are using categorical variables, we cannot calculate correlation. If the scatter plot does not look linear, then correlation is kind of a meaningless statistic here. Okay, so before you use correlation, you need to check a couple of conditions just to make sure that this is an appropriate time to look at correlation. So first is, are the variables quantitative? Second is it straight enough? And then finally, are there any outliers? Because if there's outliers, then outliers can have a heavy impact on the correlation. So first of all, quantitative variables condition. Correlation only applies to quantitative variables. If they're categorical variables, leave it alone, right? Correlation is not a thing with categorical variables. So it doesn't work, right? And don't accidentally use categorical data that looks like quantitative data. Like sometimes percents can do that. Doesn't work. Has to be quantitative data. Okay. Check the units if you're not sure. Right. Checking the units is a good way to find out if something is indeed quantitative. Is it straight enough? Right. You're gonna want to look at the actual scatter plot of the situation. Okay. You can calculate the correlation coefficient for any pair of variables, any set of numbers, but it doesn't mean anything if we don't already have some part of linearity in the data. And you can make things that have a high correlation coefficient that are not linear at all, and I will show you guys that in a little bit. Okay, so it only measures the strength of linear associations, and that number will be misleading if it's not linear. Finally, the outlier condition. Outliers have a very strong effect on correlation. A single outlier can change the correlation coefficient by a significant amount. So it can hide big. It could be something that has a good correlation that the outlier messes up, or it can make something that does not have a correlation look like it does. So outliers really ruin things. So you have to make sure that things don't have an outlier. In fact, they can go so far as making something that is positive become negative, and that has again a huge effect on the overall correlation. So if you do have something with outliers, it's a good idea to check it with the outlier and check it without the outlier to see how strong of an impact the outlier is having. Okay. So conditions, as long as those are met, we can calculate correlation. So let's talk a little bit more about various properties of correlation. So first of all, the sign of the correlation coefficient gives us the direction of the association. Meaning, if it's -1, that is a negative association, right? Its direction is negative. If it's a positive one, that means it is a positive number, okay? It can be exactly equal to -1 or 1, but that's unusual because the only time it'll have a correlation of 1 is if the data falls in a straight line. Like all points falling in a straight line would be a correlation of 1. So it's very rare to see that in real world data, but it can happen. A correlation of 0 corresponds to a weak linear association. So a big scatter of points would be 0. Okay, so correlation between -1 and 0, numbers closer to the 1s are stronger than closer to 0. All right. We also treat correlation treats x and y symmetrically, meaning that if you were to take a graph, x-axis, y-axis, and have some kind of thing here, right? And then you were to flip the x and the y, change it like this, the correlation will not change. It treats it symmetrically. So flipping the x and the y like that doesn't actually have an effect on the correlation. Correlation does not have units. It is simply a number between -1 and 1 that reports strength. Correlation is not affected by changes in the center or scale of either variable. So changing it to z-scores, changing it back to your units, none of that has an effect on the correlation coefficient. Because it depends on z-scores, and z-scores are unaffected by that, it doesn't get affected. Correlation measures the strength of the linear association between two variables, which we've said. They can have strong associations, but still have a small correlation if the association isn't linear. And I'm going to show you an example of that here in just a moment. And then finally, correlation is sensitive to outliers. A single outlying value can make a small correlation large or a large one small. All right. So let's go to a little app here, and we will show you some things with correlation, because this is going to load. Okay, here we go. So here we've got our graphing area, and we're going to add points. Okay, so there's 2 points. Notice that these 2 points form a straight line. So my correlation currently is -1. But as I add more points, you can see the correlation coefficient changes with every point that I add. And I'm adding points that are all kind of scattered and in a straight line. So you will notice that the correlation coefficient is staying fairly close to -1. Right? But let's add a big ol' outlier. Look at the dramatic change that happened. It went from -98 to -72. Adding one way up there, look at how much massively that changed it. So big outliers cause big problems to correlation coefficients, right? We can have correlations that may be curved and still be relatively high, right? Notice how this is very clearly a curved line. and yet there we have a negative 0.91. This is not linear, it's curved. But because of sort of the weaknesses of the calculation, it still appears to be that way. You can also say, if we were to curve this back up, notice that as I curve it back up and form a parabola, there is very clearly an association between these, but it's not linear, and that's one of the reasons why that's showing so low. We can scatter it more in a positive direction, and you'll see that we're getting something not quite as strong this time. Right? The more scatter we kind of put out here in that linear direction, the lower it kind of goes. Still clearly very positive and linear, but not nearly as strong. Or we can just make a complete scatter, and you will see in a complete scatter of just a sneeze on the page that we definitely do not have an association. All right. So I'll put a link to this to this little applet if you want to play with it down in the description, so you can go check that out. But let's go ahead and finish off these last couple things here. So finally, the last thing here is correlation does not equal causation, and this is one of the biggest fallacies that people make about statistics, is that they see a correlation between two objects and they automatically assume that that means that one caused the other. Right? If we have a strong correlation and we see a clear linear relationship between the two, we want to make this connection that the predictor variable caused the response. But we have to be careful, because scatter plots and correlation never, ever prove causation. So I'll give you some examples here of things that why this is such a problem. But it doesn't prove causation, because this is just, there may be two things that have a relationship, but the actual causing variable we're not measuring, and we call that a lurking variable. It may be that we're confusing what's actually causing it. So scatter plots never prove causation, and here's some good examples as to why. So for example, there is a strong positive correlation between the number of firemen at a fire and the amount of fire a damage does. Excuse me, I'm going to damage a fire does, right? Which, if we say that means that firemen cause damage at fires, the solution is that when we have a big fire, we send less firemen, and then it won't cause as much damage, which is obviously wrong, right? There's a correlation between these, because big fires need more firemen, but big fires cause more damage. It's not the firemen that are causing the damage, it's the size of the fire. And so both of those things, the size of the fire is going to have large increases in both damage and number of firemen. So these two variables will be related, even though it's the fire that's causing the damage. There is a strong negative correlation between the amount of tutoring received and grades received. Solution: never get tutored, and then your grades will be higher, right? Because the more tutoring you get, obviously the lower your grades are. And so that's bad. Just don't get tutoring. And that's obviously terrible advice, because it's not the tutoring that's causing grades to be low. It's the fact that, generally speaking, people who need more tutoring are getting lower grades. And that's because of a lack of knowledge, not a lack of tutoring. So it's not causing, but there is a relationship between them. There is a strong positive correlation between the number of drowning deaths and the sale of ice cream. And this is true, right? As the sale of ice cream increases, or excuse me, as the number of drowning deaths increases, so does the sale of ice cream. And it's not because ice cream is causing drowning deaths, or vice versa. People don't drown and then go eat ice cream. It's not because of that. It's because people don't eat ice cream in the winter as much. And people don't drown in the winter as much because people aren't swimming in the winter. But in the summertime, both people swim more and they eat ice cream more, and therefore there's increases to both of them. But obviously, eating ice cream or having ice cream out there is not causing drowning deaths, even though that there's a strong positive correlation between them. Correlation does not equal causation. Here's a fun one. Here's a graph of the number of storks. This is a study that came out of, like, I think it was Germany or something. It's a European country. I can't remember which one. But they found that the number of storks in an area was positively correlated with the human population of an area. Conclusion: the storks are bringing more babies. The more storks there are, the more babies show up, right? Because that's how babies are made. The stork comes and drops the baby off, and everybody knows that, right? Obviously. But we know that that's not true. And so hopefully at this point, if you're taking this class, you know how babies are made. It's not by a bird. We'll leave the details of that to a different video and teacher and subject. But why is there a positive correlation here? Well, it's because storks eat human trash. And so the more humans that are around, the more storks have food source, and so therefore there's more storks. It's not that the storks are causing a higher population. And finally, my favorite one. I like the concept, but it's a terrible graph. Like, first of all, don't look at the scaling. The scaling is just miserable. It makes me want to punch somebody. And also, yeah. But here we can see that decreasing pirates is causing global warming, right? The average global temperature is going up as we lose pirates. And so clearly pirates are preventing global warming. And so we need more pirates. More pirates save global warming, and we all get to live a bit longer, right? Clearly the only explanation. So, all right, that's everything we have for correlation. And so we'll do that problem some other time. That's everything we've got for correlation. Thank you guys very much for watching. I hope you have a good day. Bye.